Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Today, our group are presenting physics for the topic energy conservation in modern architecture. So here are the table of contents. The first one is introduction. The second one is objectives. The third one is concept of energy conservation or theory. The fourth one is related formulas to application in modern architecture. The fifth one is renewable systems for energy conservation and conversion. And the last one is real life application of energy conservation in modern architecture. So here are the introduction. So energy conservation in modern architecture revolves around optimizing energy use, and minimizing waste through innovative design and technology. The core objective is to create buildings that are energy efficient while maintaining comfortable, healthy living and working environments. By integrating these principles, modern architecture strives to achieve a balance between aesthetics, functionality, and sustainability. This approach aligns with global efforts to increase efficiency of energy usage and reduce energy consumption. Architects and engineers collaborate closely to deepen their understanding of energy conservation principles, ensuring that each design maximizes efficiency and reduces wastage. So, in conclusion, energy conservation in modern architecture aims to balance aesthetics, functionality, and sustainability by optimizing energy use and reducing waste. Through innovative design and technology, architects and engineers work together to create energy-efficient buildings that maintain comfort and health while supporting global efforts to enhance energy efficiency and reduce consumption. So the objectives of this presentation, the first one is to examine the principles of energy conservation in modern architectural designs and construction practices. The second one is to analyze the role of energy saving practices in modern architecture. The third one is to explore the physics concept used in modern architecture. And the last one is to better understand the why certain physics concepts are used in designing spaces and building to conserve energy.
And now I am going to talk about and explain about the key concept regarding this topic we are discussing. What physics rules are related to the energy conservation in modern architecture? How does the rule implement? And that is what I am going to explain today. First and foremost, if we look closely at this topic, we would realize that we are talking about energy conservation. And when we talk about energy conservation, it is actually related to one physics law or one physics concept that we have learned during our secondary school, which is the thermodynamic law of energy conservation. So, what is actually the thermodynamic law of energy conservation? This law actually stated that energy cannot be created or destroyed. It only can be transferred or converted from one form to another one. For example, when we pull a band, it is actually a transformation from potential energy, and when we release the band, it turns the energy into kinetic energy. So that is basically what thermodynamic law of energy are. Energy efficiency in building is about reducing unnecessary energy transformation and minimizing energy loss. Energy efficiency in modern architecture is also about how we maximize the usage of natural energy such as wind and sunlight. To prove that this theory is related to our topic today, I will show you one simple example of how we implement this theory into real life situation. Let's talk about the solar panel used by many houses nowadays. This is a really good example of energy conservation law. The solar panel convert the sunlight from the sun into electricity, which convert a natural source of energy into electricity, which will be used for many things. So the natural energy here, which is the sunlight from the sun, is used to the maximum. If we are looking at a wider perspective, we can also relate this law into the heating and cooling system of a building. Architect will use this law of conservation of energy to design a ventilation system which minimize energy loss. Let me give you one example of how we implement this theory into heating and cooling system in modern architecture. For example, we have two buildings, building A which have less window than building B which have more window. So clearly, we would know that building B will have a better air ventilation rather than building A. To explain this is actually very simple. This is because building B will have better air ventilation because it uses natural air, or we can call it natural energy, which is the wind. On the other hand, building A will need to use such thing as fan, and we all know that fan needs electricity in order to work. So to have this electricity, we will have to have a new source of energy, which will be a waste of energy. So the conclusion is the building B with more window are using less energy, and this is the actual example of how we can conserve energy. Next, when it comes to energy conservation, we can also talk about energy efficient materials. Architect will choose the best material which use less energy. Architect and civil engineer will work alongside each other and calculate the heat transfer of some materials and choose the best materials that can conserve the maximum energy. When we talk about energy conservation in building consume energy primarily through heating. So how does the heat went through a building? There's four ways of how heat went through a building. The first one is conduction, heat moving through walls, window and door. The second one is convection, heat moving through air inside room. The third one is radiation, sunlight entering through window or heat loss from exterior surface. The last one is insulation. It works by showing conductive and convective heat flow. So the small conclusion that we can make from this part is the law of energy conservation, which is the key part of this topic, is essential for understanding how energy can be conserved in the best way possible and how we can maximize the usage of energy so that it wouldn't go to waste.
So now we will discuss the related formula with energy. It is important to know related formula with energy to analyze on how to conserve the energy. So the first formula is energy efficiency formula. This formula is being used to calculate the energy efficiency in systems. The formula is energy output is divided by energy input multiplied by 100. So we get the efficiency. The answer will be in a percentage. Energy output is the amount of energy that comes out, while energy input is the amount of energy that put into a device. A high percentage of efficiency means less energy being used, so it is good because we can reduce the cost. So next slide is energy demand of HVAC systems. HVAC stands for heating, ventilation and air conditioning. The formula is E is equals to Q divided by COP. A is energy required in kilowatt hours, Q is cooling or heating load in kilowatt hours, and COP is coefficient of performance of the system. So this formula is used to calculate the energy required to meet HVAC system demand. It is important to know how much energy is needed so we can plan how to minimize the amount of energy required and plan to improve efficiency. So this means a higher COP means more efficiency. It is also indicates that the less usage of energy being used. So next slide is energy consumption. The formula is E equals to P multiplied by T. E is energy, P is power, and T is time. Energy consumption means the total amount of energy that being used. It is important to know this formula so that we can monitor the amount of energy that being used. The next one is solar gain. The formula is Q equals to capital A multiplied by A and multiplied by I. So Q is the solar gain, A is area of glass, A is absorptions, and I is solar irradiance. So solar gain refers to the increasing of heat of an object in a space that results from observed solar radiation. For example, when the sun shines into solar panels, energy from the sunlight is being absorbed. So the next one is coefficient of performance, COP. The formula is COP is equals to heating or cooling output divided by energy input. So basically COP is a ratio that describes the efficiency of a system. So the higher the COP, the more efficient the system. The next one is net zero energy equation. It is energy in is equals to energy out. So energy in is the total energy that being generated, while energy out is the total of energy that being consumed. Usually net zero energy refers to the building that produce energy as much as the energy that being used. Next slide. Energy efficiency ratio, EER. The formula is EER is equals to cooling output. It is in BTU per hour and divided by electrical input. It is in watt. So EER is being used to measure the performance of an object. If EER is higher, it means that the efficiency of an object is higher. The next one is thermal conductivity, it's the U value. So U is equals to, the formula is U equals to 1 divided by R. So R is the thermal resistance of building materials. Thermal conductivity is the ability of substance to conduct heat. It means that the lower the thermal conductivity, then it is better. It is because the materials conduct least heat energy. Last but not least is heat transfer. For Fourier's law, the formula is Q equals to K multiplied by 8 and multiplied by the changes of T divided by D. So Q is heat transfer, K is the thermal conductivity, A is area, the changes of T is the changes of temperature or temperature difference, and D is thickness. So heat transfer is the movement of an object, the movement of heat from one substance to another substance. It is flows from a high temperature object to a lower temperature object.
Okay, Assalamualaikum. So for my part, I will be talking about the real life example of energy conservation in modern architecture. So for the real life example that we found in our research for our presentation is the IRENA headquarters, which is the International Renewable Energy Agency headquarters, which is located in Abu Dhabi, UAE. So why did we choose this building as an example of good energy conservation in modern architecture is
because the building it incorporates many design elements that is focused on energy recovery system and energy efficiency. So from this, we can understand that the architects and the civil engineers behind the design of this building have a thorough understanding on energy conservation and the physics concept, such as the first law of thermodynamics, which means that the first law explains that energy cannot be created or destroyed, but is changed in another form. There are many key features that are found in this building, but for our presentation, we will only focus on a few features, and the features we found through our research online. So from our research online, we found that the building have a solar water heater, and the solar water heater actually provides up to 75% of the hot water demand in the building. So from this, we can see that the hot water heater actually uses renewable energy sources and not from a power plant like a coal power plant which uses non-renewable energy source like fossil fuel. And the second feature I will talk about is how the building is 2 times more airtight than a regular building. So for regular building, the International Renewable Energy Headquarters usually require it to be at a certain height of airtightness. But for the headquarters, they actually design it to be 2 times more airtight so as to increase its energy efficiency and to reduce energy loss through for example through air conditioning air loss. So another feature is the air conditioning system actually recover 75% of energy release through the exhaust. So from this, I will explain it by saying that the exhaust is used to actually cool incoming fresh air that is coming into the building. So from this, we can see that they actually use the energy from the exhaust air to cool down the fresh air coming inside to the building. So we can see that from this example of the real life application of energy conservation in modern architecture is that this example uses passive design and active design to manage the energy loss and energy acquired. So for example, the building through active design is, for example, like smart energy management, which is through a computer regulated thermostat, for example. And for passive design, it might be how they design the windows. And from the combination of both, we can see that they found out that up to 45% of the energy, 42% of energy is actually lesser than the energy needed compared to global energy efficiency standard. So we can see that this building is more energy efficient than any building across the globe. So since it's more energy efficient, it uses 42% less energy than a normal commercial building would, like for example a mall. So we can see that the energy conservation is better through the use of smart and passive design.
Alright, so for the last part of our presentation, I'm going to talk about the summary or the conclusion. So for our presentation, energy conservation is a critical aspect of modern architecture addressing the urgent need for sustainable building practices in response to climate change and resource depletion. This folio explores the principles, strategies, and innovations that contribute to energy efficient designs in contemporary architecture. In conclusion, energy conservation in modern architecture is not merely a trend but a vital movement towards a more sustainable future. By prioritizing energy efficiency, architects and builders can create structures that benefit both occupants and the planet, paving the way for a resilient built environment. And also, by employing strategies such as passive design, advanced insulation, renewable energy integration, and smart technologies, architects can create energy efficient structures that minimize resource use while maximizing comfort and functionality. These efforts not only reduce operational costs but also contribute to a lower carbon footprint, making modern architecture a key contributor to global environmental goals. The future of building design lies in balancing aesthetic, functionality, and sustainability to ensure a more energy conscious world. So, the references for our presentation from printed book, we use our college physics books, the global edition one, which is the 12th edition. For the reference from online sources, we use websites such as National Academies Press, International Renewable Energy Agency official website, and the ResearchGate. So I think that's all for the presentation from our group. That is about conservation of energy in modern architecture. Thank you, sir, for listening to us.